how do we make geothermal a major player? And I think that geothermal is that missing part of the puzzle that solar plus wind plus other renewables can't quite fill.
Greetings, Earthlings, and welcome back to Earthlings 2.0, the show where we imagine how we can be better versions of ourselves and build a collective future we actually want to live in. Today, we're exploring the frontier of renewable energy with a company that is unlocking the vast potential of geothermal power, meaning you wouldn't have to have special typography at a specific location to make geothermal viable. Instead, this technology from Quaise Energy might open up nearly any location to accessing the Earth's heat for power. And they're going to do this by utilizing gyrotron-powered drilling platforms and basically vaporizing rock. So you can get to really unprecedented depths where temperatures exceed 400 C. This is a breakthrough that could provide virtually limitless sources of power and baseload energy. But before we get into the details, I'm your host, Lisa Ann Pinkerton. I'm the CEO of the award winning PR firm Technica Communications and the founder of Women in Clean Tech and Sustainability. Prior to this, I was an award winning environmental science reporter for NPR and PBS. And whether this is your fifth or 50th episode, thank you so much for joining us each week. We deeply appreciate you spending time with us and giving us the opportunity to bring you really cool stories like this one. If you would like to get more involved in the Earthlings 2.0 world, we encourage you to take our listener survey so that we can understand more deeply the types of stories that you like to hear. So you can get hit up only once a month on the roundup of shows that have been happening and series of shows that are good for binge listening. And also, you can join our Patreon page and become a member and support us financially. If you've done all of those things, or if you don't feel like doing all those things, that is perfectly okay. One thing I would ask you to do beyond all of that is to share this show with a friend. Spreading the word about the podcast is truly the most effective thing that you can do to give back to the podcast. And thank you to Resource Labs for having us on the network. Now, geothermal energy has long been limited by depth and temperature of which we can reach with conventional drilling methods. However, Quaise Energy is changing this narrative by advancing a very specific type of technology which promises to tap immense heat deep within the Earth's crust. This approach not only aims to generate power more efficiently, but also repurpose existing fossil fuel infrastructure. But before we get into this discussion, a quick 101 on some enabling technology. Quaise Energy's innovation utilizes gyrotron technology. Now, what are gyrotrons? Okay, these are a type of high power vacuum tubes that generate millimeter wave electromagnetic radiation by using the cyclotron resonance of electrons moving through a magnetic field. I know that was sounds like a lot. Let me rephrase it for you. So what this means is as electrons spiral, they create electromagnetic radiation at millimeter wave frequencies. This can apparently melt rock, and gyrotrons make that happen. Our guest today is Trenton Cladouhos. He's the Vice President of Geothermal Resource Development at Quaise Energy. He's spent 35 years in applied geosciences, with the last 15 in the geothermal industry. He's worked on geothermal projects worldwide, including EGS, geothermal exploration, drilling, and well field operations. Trenton, welcome to the show. To kick us off, what inspires you to work in geothermal energy?
So when I was an undergraduate at Stanford in the late 80s, I had a part-time job at the USGS in Menlo Park, and I worked with Art Lockenbrook, who's one of the geophysicists, world-renowned geophysicist, who worked on heat flow. And I studied what I worked on with him was looking at temperature profiles in permafrost in Alaska. And this the study that we completed showed that there was an early signal of global warming back then. And so I became a believer in geothermal, or in sorry, I became a believer in global warming back at the very beginning of my career, and knew that we had to do something to reduce the burning of fossil fuels and and find alternative methods of generating electricity. So I started in the geothermal industry in 2008 at Altarock Energy. I've also worked at conventional geothermal companies. And what I've learned in the geothermal industry is that, it's currently it's a wonderful way to generate electricity. It's baseload, it's low impact, but it's going to remain in a niche unless we do something to change that. And so I think that one way to change the game for geothermal, make it globally scalable, is to go deeper and hotter to create a higher quality resource.
But I like that you mentioned that because it is um, still pretty rare around the world, and it feels like it's a bit of an untapped resource. So can you explain to us, where is the industry today in terms of generating energy from geothermal heat?
So it is an untapped resource because everywhere you go on the Earth, it gets hotter as you go deeper, and on average about 30 degrees Celsius per kilometer. So you have to find, and so that's not a very high gradient. So you have to find places where there's some geologic conditions that bring heat closer to the surface. So that's in volcanic areas, so all around the Ring of Fire. In areas with thin crust and active tectonics, that's areas like Nevada and Turkey and Eastern Africa. So those are the areas that we currently have conventional geothermal systems. Famously, geothermal electricity generation started in Italy way back in 1904, so it's been around for a long time, but it's at only about half a percentage of global energy electricity production. So it's a small part of the overall energy mix. More recently, there have been some great successes on extracting heat and energy from areas where there is hot rock but no natural permeability, so no fluids to drill into. So you have to make the engineered geothermal system or the permeability. And there's been some great successes there just within the last couple of years. So it's pretty exciting. But these new projects have not yet been proven out in the long term, either economically or technically. And so I think we're all waiting to see how those projects work out, but also finding ways to start from a more economic design.
Could you lay a baseline for us? How does geothermal energy work today?
So to do a geothermal energy project, you just need to drill wells in a conventional area into hot water, and then usually that water will either, or steam, will flow out of the well on its own, or you may have to pump it with large pumps. And then you send that water through a geothermal power plant of some sort. There's a couple different flavors, but generally you're using that hot water to spin turbines, which spins a generator and generates power. And then you take the fluid that you've extracted the heat from and you re-inject it. So at a minimum, you have two wells generally, but most projects have 10 or 20 or even 100 wells, all connected in the subsurface, where that cool water you re-inject finds its way through the rock to a production well and then to the surface. So in a hydrothermal system, you don't have to create any of those pathways. They're already there. It's just a matter of drilling into them in the right spot. So in the case of where there's hot, dry rock or no permeability, you have to create those pathways between the two wells. And so that's what I've spent my career doing, is trying to develop the technology to connect two or more wells to each other, an injector and a producer, in order to basically mine the heat out of the rock with artificial pathways.
And are these projects that are in existence today, are they at a utility scale? I know there are a few sort of private commercial scale plants. What are we operating on?
So they're definitely utility scale. Some of the largest power plants in the world are 300 megawatts. in some plants like that in Africa and Iceland, some of the largest plants. So they go from 300 megawatts all the way down to 10 or even 5 megawatts, which would just be a couple wells. Probably the average geothermal power plant's around 50 megawatts. So they're pretty large. They're owned either by overseas, they're usually owned by utilities. For example, in Iceland, the city of Reykjavik owns a couple geothermal power plants. In the U.S., it's not as much utilities as independent power producers who sell to utilities through power purchase agreements.
And as I understand it, Quaise Energy has discovered a way to make geothermal energy more accessible to more areas of the world. What was the problems that the company was working on that then led them to this interesting technology development?
The technology comes out of MIT. There's a professor there who was using gyrotrons to create millimeter waves, and he realized that they could be used to vaporize rock. And then so it kind of became at that point he brought that to Altarock Energy, where I was working previously. He said, I've got this new drilling technique. Do you think it might be useful in geothermal? And our initial reaction was, well, we don't generally need to drill as deep as this technique would allow. We can use conventional drill bits to drill to the depths that we're interested to in the western U.S. But then, we got to thinking about it more and realized, well, this is a way to drill not to just 5 kilometers, which a conventional geothermal drilling project might do, but 10, 15, or 20 kilometers. And so once you can drill that deep, you can scale geothermal globally. So you can go to, Pennsylvania, drill down into the basement, say at 15 kilometers depth, and reach a temperature of 350 degrees C. And now you can produce that heat and have economic geothermal in a place that no one's really thought about doing geothermal before. So the millimeter wave really enables a global scaling of geothermal, beyond the conventional areas that geothermal's done.
That's a lot to unpack there. So for people who aren't as technically savvy, can you explain to us what gyrotrons are?
So gyrotrons were developed for fusion technology to create the heat and the containment fields necessary for fusion. And they produce millimeter waves, which are a portion of the electromagnetic spectrum between microwaves, which we use for cooking, and infrared, which is heat, heat. And millimeter waves are used in many different applications like airport scanners, 5G phone connectivity. And so the key is that when millimeter waves hit rock, they cause dielectric heating of the rock, just like when we cook food, it's dielectric heating of the water in the food. So the same thing at these millimeter wavelengths, it causes a dielectric heating in the rock, which will vaporize the rock, or spallate the rock, or break it up basically by heating it rapidly.
It feels kind of like how, I don't know if anybody's ever had a hot crafting rod, and then you stick it in plastic and it just melts a big hole in the plastic. Sounds like that's basically what you're doing, but on a huge scale to melt this rock.
In place of that rod, think of it's called a waveguide, and so it's like drill pipe, although specially built drill pipe that we send the millimeter wave down and hook it up to a regular drill rig, this waveguide, and then at the tip of that waveguide, the millimeter wave comes out and vaporizes the rock, and then we are also pumping purge gas, most likely just nitrogen, down the hole. That purge gas lifts the dust out of the hole past the waveguide, and then the waveguide just keeps going, marching down the hole, vaporizing rock and sending the dust back to the surface as we go. So the key advantage of drilling in this way is that we don't need to use a drill bit. Drill bits, wear out, say within, say 500 meters typically. the drill bit will last. And it gets worse and worse as you get hotter and harder rock. So we eliminate the drill bit, and every time you have to replace a drill bit, you have to trip all the way back to the surface and replace it. So tripping out of the hole can take, on deep holes, more time than you're actually drilling. You're spending more time replacing bits than you are drilling. So there's no, in the case of energy drilling of any sort, you're not having to trip out of the hole to replace any worn out gear. There's nothing down hole to wear out.
So when we're looking at this technology that Quaise has built, what have you accomplished so far with it? Do you have? I read that you have a pilot demonstration facility that you're using.
So at our lab in Houston, we've drilled about 9 feet through a column of granite, about a 2-inch hole. And the next 2 milestones are to connect it up to a large conventional rig, a gyrotron and a waveguide, and do a demonstration just in a testing facility. And then also drill about 100-meter holes in a quarry using a smaller rig and waveguide. So those are our next 2 milestones. And then after that, we'll be looking to drill commercial-sized holes using the pieces we've developed.
What are the commercial sizes, the commercial size hole?
So, our goal is to drill. We think that at about 5 kilometers is where millimeter wave drilling starts to beat conventional drilling as far as rate and cost. So the idea is we drill conventionally down to, we're not sure exactly, 3 to 5 kilometers, say, and then we start millimeter wave drilling. So our initial holes might be about 10 kilometers deep, and usually the goal is about an 8-inch hole. That would be a typical geothermal hole size, and 8 inches in diameter.
How much energy is required to vaporize this rock?
So the gyrotrons, they kind of come at 1 megawatt's about the biggest it's been designed. That's probably about the amount of energy. Maybe we need 2 megawatts, so we could have two gyrotrons actually at the surface connected to a single waveguide, and that would be enough energy to drill at about 5 meters an hour at these depths. And so that's actually, it sounds like quite a bit of energy, but a conventional geothermal rig uses about that same amount of, using electric generators, say 2 to 4 megawatts of electric generation to drive the conventional geothermal. So it's not a lot more, or it's a similar amount of energy as conventional drilling.
Yeah, because I can imagine if you're looking to create a geothermal energy plant somewhere, that means you don't have grid power, and so you got to bring that power with you to the site, and that's in the form of.
Yep. Yeah, usually diesel generators. That's what's used in conventional drilling as well.
How do you envision geothermal energy mixing with renewable energy sources as we continue through the energy transition?
So, I think solar and wind are doing their part now in making a large impact. But if we really want to decarbonize fully, especially in certain places that don't have wind and solar resources, we need something to replace the fossil fuel burning that's occurring now. And so that's where geothermal comes in, is really a clean, firm energy source that has the kind of efficiency and of fossil fuels. So it's not necessarily competing with solar and wind. It's going to be places where solar and wind can't get us to full decarbonization, which is most places.
So when you're looking at expanding and building out your technology, you talked a little bit about what's coming next. What can we expect from Quaise Energy this year and the next couple of years? Like, what's your timeline?
So yeah, we're starting to do field testing this year and next of the drilling system, but there's really a second path or parallel path of challenges we need to work on, and that's actually my expertise, is the enhanced geothermal systems, or EGS. So basically, once we've got a well, how do we create a reservoir or a pathway to a second well? And so we're going to be developing plans and doing a pilot project also for EGS. That'll likely be in a place with high gradients, so we only need to drill maybe to 4 or 5 kilometers. So we won't use the millimeter wave in our first geothermal project, but we'll use conventional drilling and create enhanced geothermal system at temperatures above 300 degrees C, say 300 to 400 degrees C. And so that's the other part of the Quaise plan, is to do geothermal at much higher temperatures than anyone else is doing. And the advantage of higher temperatures is just more energy per well. So conventional geothermal wells, or say at 200 degrees C or 400 degrees F, that well can produce about 6 megawatts per well if you're at that temperature. Once you get up to higher temperatures, you get to 375 degrees C, you can have a well that'll produce say 20 to 40 megawatts per well. And so, wells are expensive, so you want to minimize the number of wells that you drill. And one of the easiest ways to do that is to drill hotter. So we're going to be working on doing, we call it super hot rock, and to distinguish it from, what the EGS other companies are working on. So that's one way to really improve the economics of geothermal, by producing more power per well.
Yeah, so let me make sure I get this right. Because you can go deeper, you can access hotter water or hotter temperatures that can create hotter water, that then allows you to create more energy from that well.
Yeah, yeah. So you can produce, instead of producing water, you can, with an enthalpy of about like 700 kilojoules per kilogram, we can produce superheated steam with enthalpy of say 3,000 kilojoules per kilogram. So the water just contains more energy. And then the other part of it is you can send that through a more efficient power plant. So you can now you can take that superheated steam and send it through a turbine, steam turbine, which is much more efficient than other types of system, like a binary system.
Yeah, I think in the past people have sort of thought, oh, geothermal energy, that's cool, but it's just not applicable everywhere. And so it's always going to sort of be sort of on the sidelines of the energy transition. But what you're building here allows it to be much more of a major player.
Yeah, well, it has been a little bit on the sidelines, but yeah, that's the whole point, is how do we make geothermal a major player? And we need some solution to decarbonize, right? And I think that geothermal is that missing part of the puzzle that solar plus wind plus other renewables can't quite fill.
So looking into the future, 10, 20 years, where do you expect geothermal energy to be in our energy mix?
So I'm focused on the high temperature, energy generation. There's a lot of opportunities for geothermal all the way down to lower temperatures. There's geothermal heat pumps. There's direct use of geothermal for campus heating, for example. I think there will continue to be a place for geothermal, conventional geothermal, and it's continuing to grow. So, I'd like to see geothermal, across the spectrum of temperatures and uses. Maybe geothermal doesn't always need to be, the high temperature wouldn't necessarily need to be used for electricity. We could also use that for process heat. Right? Can you use that fluid directly in a factory? So I think just the idea of using geothermal kind of everywhere for as many applications as possible, and getting out of the half a percentage of electricity generation up to 10-20% possibly.
Well, thank you very much for being on the show with us. We covered all the questions that I wanted to talk about. Is there a question or that you thought I'd ask that I didn't, or a piece of information that you wanted to share that you haven't shared yet?
Sure. Some of the other things that I guess criticisms of or problems that are considered for geothermal. One of them is water use. So we do use water for creating reservoirs, and also we circulate water through our EGS in order to generate power. But that water is used in a closed loop, so there shouldn't be much water consumption. We also don't need any sort of high quality, drinking water. The water we use doesn't need to be potable, and so water use isn't really an issue, and because of we don't consume the water. We just use it in a closed loop. The other problem that gets talked about in geothermal sometimes is induced seismicity. It's been the case in a couple projects in Europe and Korea where small earthquakes were created due to EGS creation. That's an area that we need to continue to research, monitor, but we've made a lot of progress in the last 10 years on understanding how induced seismicity can be mitigated and controlled for geothermal systems.
Are those the similar types of small earthquakes that I have seen reported around shale fracking sites?
Yeah, so for shale fracking, it's usually disposal of the flowback fluids. So once uh, you do your frack job, you flow back the water, and then you have this toxic waste you need to dispose of. And so they usually pump that into a disposal well, and it's all pumping in. So it's just a volume increase downhole, and that can eventually create seismicity. So we're never in that instance in geothermal because we're circulating the fluid, right? So there's no extra fluid being added, especially once we're in the operational mode.
Yeah, very good, very good. Well, thank you so much for being on the show today and talking to us about Quaise Energy. We'll keep our sensors pointed in your direction, and we'll see you again on another turn of this beautiful blue-green space flower that we call home.